Okay, so let's take a look at this concept of the potential divider. There's several reasons why you might want to use a potential divider. One of the reasons would be if you have a power source that provides too much voltage and you want to reduce it down so that it can be used by some other device. This is a way that you could do that. More importantly, though, by creating these potential dividers, we can connect things to the potential divider, and by making measurements from those devices, we can do things like measure temperature or light levels. So a lot of the purpose for the potential divider, because it's actually kind of a wasteful device. I mean, it actually purposely wastes some of the voltage of the battery to step down the voltage to a level. It's not a very efficient way of doing things, but in the case where you're trying to connect this to a sensor, or you're trying to use the voltmeter as a way of measuring things, the potential divider, while not terribly efficient, is actually really good at making those measurements. So let me show you what the simple potential divider looks like, and then we'll take a look at a slightly more complicated version. We'll draw a very large circuit. With two resistors. And we need the two resistors because they are the ones who are going to do the dividing. So we'll give this guy R1 and R2 as their labels. We will assume that this battery has no internal resistance because that does actually change the circumstances just a little bit. Okay, so here's the idea with the potential divider. Obviously, these two guys share the potential because that's the rule in series, is that the resistors share. So whatever the EMF is, these guys will get a portion of it, and we can figure out real easily what that portion is because remember, the equivalent resistance is going to be just R1 plus R2. So therefore, since we know that V is equal to I times R, actually we should say EMF. We'll say the EMF. In this case, the EMF and V are the same thing, though. EMF and V are the same thing. So ultimately, how would we figure out what the I is for this thing? Well, we would need to know what the total resistance is, right? So this would be REQ. So since I is equal to V over R, we'll say REQ. Oh, I keep doing that. So sorry. We'll use the EMF symbol. They are the same thing in this case because I'm saying there's no internal resistance. So I would be equal to the EMF divided by R1 plus R2 because that's the total resistance of the circuit. And so therefore, what if I only wanted to know the resistance in V1? Well, V1 would be equal to I times R1, but I is equal to the EMF over R1 plus R2. So what I'm going to do is I'm going to write it like this. So the EMF is a different property. It's not in the same units as this guy. I'm going to pull that one out to the side. And this R1, so I'm going to have EMF over R1 plus R2, and that's going to be multiplied by R1. So we'll end up with this. R1 over R1 plus R2, there's the divider part, right? Essentially what this is telling me is what fraction of the potential is going to get used up in this resistor. Now, anyone who is connected to this resistor will also get that voltage because remember, that's the rule for parallel circuits. So they will also get that same current, same resistance and current, I should say. So this is multiplied by the EMF. Okay, and this gives us an equation now. I'm going to write it over here to the side. So this is an equation for the voltage divider. That will allow you to figure out what voltage and, more importantly, what combination of resistors is going to get you what you need. So let's say you wanted to cut it in half. Well, that's obviously very easy because you can pick any two resistors, and as long as they're identical, it's going to cut things in half. But let's say, for example, you wanted to cut it into maybe thirds. So maybe I want to cut the voltage down to 1/3. Well, just think about it. I need a resistor and a resistor with twice the resistance. Because if I have a resistor R and another resistor which is 2 times R, then when I add those two together, I'll get 3R. And now I have reduced it down to 1/3 of the total resistance, or 1/3 of the total voltage, I should say, of the circuit. So by using the right combination down here, and it's pretty, I would say almost obvious that looking at this relationship right here, the R1 over R1 plus R2, it should be really clear. This is it's a percent. It's the fraction of the voltage which is going to be absorbed or be, I should say, expended by this resistor. So it should be very logical that this is the way that it works out. Now, generally speaking, this is not as helpful. There's several places where we would want to use a thing like this, and I'll show you examples of those in just a moment. But let's first take just a peek at what would it look like. What if we wanted to be able to vary the voltage? Not only divide the voltage, but also I would like to be able to change it to any value that I want, going all the way down to 0 and up to a maximum of the EMF of the battery. Well, in order to do that, we would need to have a variable resistor. So let's take a look at a better potential divider. Oops, sorry. Okay, so I'll draw basically the same circuit. This time I'm going to draw a very long resistor. This is called the variable resistor, and it has 3 connection points, and you can actually make it work by only connecting 2 of the connection points. It actually is possible, and it will definitely work for sure. However, it doesn't have to be. You can connect all 3, or you can just connect the 2 to make it work. But it turns out that if you connect all 3 connections, that would work a little bit better. And we'll see these in the lab, so you'll get to see what an actual variable resistor looks like. But the variable resistor will have 3 connection points, so 1 on each end. So right now, this is not a variable resistor. This is just a really long, big resistor. But now I'm going to connect another resistor and there's our 3rd connection for the variable resistor. Now, what this essentially is a slider. So if you have a light dimmer in your house that slides up and down, that's it. That's a variable resistor. That's exactly what you're doing. You're sliding that variable resistor to either increase or decrease the amount of resistance in that part of the circuit that is connected to the light bulb. And by giving more current or less current to the light bulb, you can get the light bulb to turn brighter or dimmer. So not all dimmer switches are like that. There's also ones that spin, and basically all they do is they take this thing and then they just kind of curl it into so it's circular. And then the slider, instead of sliding back and forth, there's a knob on the inside that kind of runs along the top of it, and we'll take a look at those in the lab. So you'll get a chance to see what both kinds of these variable resistors look like. But now here's the important thing to think about. I'm going to go through this in detail. What happens when we slide the slider over to here? What happens when we slide the slider over to here? So let's just refer to this point as X and Y, and I'm going to refer to this point as S for the slider. So part of the advantage of doing it this way, as opposed to what I could actually do, I mean, it would actually work, is I could disconnect right here. I could disconnect this one right here, and this would still work. So the slider, as I slide back and forth, it would change the voltage that this guy is getting, because he'll be getting more or less of the voltage of this. But realize, if I take this away, then no current flows through this part of the variable resistor. The current comes out, comes to this junction where it's going to have the potential to split. Some of it can go this way, some of it can go this way. But if you don't connect this, then no current will flow in this part. It will come around, it will enter the variable resistor right here, and it'll just continue on its way out this way. And no current will flow through here. Now, no matter what I do, if I were to, for example, go all the way to the end, I would be able to get close to the maximum voltage that is available to me. But if I were to go all the way down to this end, I would never be able to get down to 0. I'll never get down to 0 because current is always going to be flowing through here. I'm always going to be dissipating energy in this resistor, which I'm going to call R1. Okay, so here's the basic idea. If I take this slider and move it all, so I do have this connected. I move the slider all the way down to the left-hand side. I will find that a voltmeter connected to this guy will say 0. Remember, the voltmeter has a very large resistance, so I'm not going to draw any current down this portion of the of the circuit. I have a current that's leaving the battery. We'll call that I. And that current is going to split into two possible currents. They are right there. And those currents are going to be, we'll say, I1 and I2. I'm actually going to change this guy's name to R2, and we'll call this guy R1. Okay, so here's what's going to happen. At X, so move the slider to X. What will happen when we do that? Well, the voltage in the voltmeter will go to 0. And the reason for that is when you slide the slider all the way to this side, essentially now you have connected this resistor to a short circuit. Because once you get all the way to the end of the variable resistor, now all there is just this little connective wire, which has either no resistance or very, very little resistance. So that means when this junction, when the current arrives at this junction, it's no longer going to go down this path. Because now I have a path that has, maybe not a lot of resistance, but some resistance. And compared to that, I have a path that has absolutely no resistance. So, in reality, it's probably not that that no current will flow down this path, but very, very little. So little that we probably won't be able to measure it. It could be like thousandths of an amp or even lower. So the result is that when we look at the voltmeter, it will go all the way down to 0 volts, which if this wire were not connected, it would still work, but I would only get down to some portion of the voltage, because without this wire right here, I can't bypass this guy. And without bypassing this guy, he's going to draw voltage. Anytime this guy draws current, there will be a voltage here. So what I need to do is to create a scenario whereby no current will go through this thing, and therefore I will receive a voltage of 0. Now, as I start moving to the right, what's going to happen is I'm adding resistance in this part of the path now. That's going to cause the current to want to go down this path a little bit more. So as I move the slider to the right, what I'm going to find is that more and more current is moving down through this portion of the path. And typically we would probably put an ammeter right about here. Sorry, I didn't draw that first. And as we start to move the slider, what we would see is that the current starts to pick up. As a result of the current picking up, the voltage is going to pick up. And when I move the slider all the way to the far right, I'm sorry, I didn't even say this, right? The voltage on R2 equals 0. And if we move the slider to Y, V will be equal to, on R2 will be equal to the EMF of the battery. Because at that point, you'll have both of these resistors will be fully in parallel. And so now they both have the same voltage, and that voltage would be equal to the voltage of the battery. As long as there is some portion of the variable resistor that is over here, this part is connected in series. Because remember, right, the junction's not here. There's no junction here. The junction is right here. So the current, as it's coming, will go like this, or it can come through R2, and then it will recombine at the variable resistor, and then this portion, all of the charges have to go through this. So whatever portion I have between S and Y, all the charges go through there, so that part is in series with the battery. And so as a result, we're going to lose a little bit of the voltage. We will not get the full value of the voltage. But all we need to do is bring that slider all the way out to Y, and we will end up getting the voltage all the way up to the EMF of the battery. And the whole reason why we're doing this is because we're trying to test out the resistance, or it's usually referred to as the IV characteristics. We want to see, what are the IV characteristics? Is this an Ohm's law object, or is there something else going on there? And this is a way to get a very wide range of data, because I can go all the way from 0 volts all the way up to the maximum possible voltage. And because I can do that, I'm going to really get to see what this circuit does and see whether it follows Ohm's law or not. Okay, so here's the deal. There are two types of devices that we could replace this R2 with. So R2 could be an LDR. Oh, I'm sorry. An LDR. That is a, let me give you the, what page this is on. This is on page 327 in the book. An LDR is a light dependent dependent resistor. So we have been able to produce resistors that when light strikes them, their resistance changes. And because their resistance changes, we can use that as a way of measuring how much light there is. So essentially what happens is R2 will get replaced with this LDR, and this variable resistor can slide back and forth, or it doesn't even need to. We can just connect the LDR back in this one. So I can just put the light emitting or the light dependent resistor around this guy, and then I'm going to connect the voltmeter to it. And essentially the voltmeter is going to tell me whether I get any light. So in the case of the light dependent resistor, generally speaking, when there is a lot of light, the resistance is going to be pretty low. So the resistance is going to be reduced because the light is actually providing energy for the charges to move. So they don't really need as much energy from the battery. So as the light allows the electrons to begin flowing, the resistance is dropping down to very, very low. And as a result, as the resistance drops very low in this guy, the voltage is going to increase. And based on the voltage measurement here, we can use that to determine how much light. So when the voltage reads the battery's voltage, then essentially we have a lot of light. It's extremely bright. We've lowered the resistance and now we're drawing tons of current from that battery. But as the light dependent resistor is put into an area where it starts to get darker, then what's going to happen is the resistance is going to begin to increase. As a result, the voltage is going to begin to drop on there. And so essentially what we do is just like with the thermometer. Just remember how we did the thermometer. We don't measure temperature directly. We measure it indirectly by seeing its effect in other objects, particularly the expansion of alcohol or mercury, or this. This is another way of doing it. So by having a sort of a proxy, something that is connected, and by running tests, we can figure out at what voltage corresponds to what light level. So based on the voltage will directly translate into a light level. So it might say, and we'll talk about the units for this, but it may give you units of intensity, and that is simply by reading the voltage. By reading the voltage on the second resistor, on this guy, we can then know how much light is striking this thing. We just have to run the test and figure out at what voltage do we get what amount of light, and now this thing has become a light detector. And this is exactly the same thing, that you would see like in a disposable camera, or essentially you need something that can be very easily measured. So we're simply measuring the voltage, and it turns into the amount of light. So it's very, very simplistic device, very, very reliable device to determine that. Now there's also R2 could be it's called a thermocoupler. Thermocoupler, and it is basically the same thing. So essentially, if you have a resistor, there are a number of resistors whose resistance depends very much on their temperature. That should make a lot of sense. I mean, because most objects, their resistance changes as they get hotter or warmer. So as a result of using this thermocoupler, we can measure the voltage on the thermocoupler, which is going to be right there. And as it gets hotter or colder, it will change the voltage. So again, we'll do the same thing. We won't measure the temperature directly. We'll measure the voltage on the thermocoupler, and that will get converted because we will already have tested it out to know at what voltage corresponds to what temperature. And so what's actually happening in an electronic thermometer is it's measuring the resistance that is in the tip, right? Wherever the thing that's measuring the temperature. It measures the resistance of that thing, essentially by getting the voltage, and that is then directly translated into the temperature. So very easy to use device, much more convenient than having to use the devices that expand. So, this does show up on the IB exam. It for sure, it is definitely a part of the IB exam. But I think that if you at least have the basic understanding, even if you don't remember whether it should have big resistance or little resistance, that's not as important as understanding that this device is a way of making measurements of light and temperature by using this electrical system, which is very reliable, very cheap, super easy to make. We can produce thousands, and they work so well in a wide range of circumstances. That's really probably the most powerful use of the voltage divider.